In the 2nd century before the Common Era, a man walked into a temple on the outskirts of Alexandria and dropped a coin into a metal slot. There was a pause, a mechanical click, and then, from a spout beside the entrance, a measured stream of holy water poured into his cupped hands. He washed, he prayed, he left. He had just used a vending machine, not a metaphor for a vending machine, not something that resembled a vending machine. An actual coin-operated, gravity-powered, mechanically regulated dispensing device, engineered, built, and deployed in a public temple more than 2,000 years before the first modern vending machine appeared in London in the 1880s. The inventor's name was Hero of Alexandria, and the holy water dispenser was, by a wide margin, the least impressive thing he ever built. Hero built machines that opened temple doors when a fire was lit on an altar. He built a miniature theatre in which mechanical figures acted out an entire dramatic performance, complete with scene changes, moving backdrops, and sound effects, without any human intervention. He built a device that harnessed the power of steam to spin a metal sphere on an axis, a machine that historians now recognize as the first known steam engine, built roughly 17 centuries before James Watt filed his famous patent. He built singing mechanical birds. He built a mechanical servant that poured wine when a cup was placed in its hand. He wrote detailed treatises describing the construction of dozens of these devices, complete with diagrams, measurements, and operating instructions. And Hero was not even the first. He was building on a tradition of Greek mechanical engineering that stretched back at least 4 centuries before his time. A tradition so advanced, so sophisticated, and so thoroughly forgotten that when modern historians rediscovered it, many simply refused to believe it was real. This is the story of the ancient automata, the mechanical beings of the Greek and Hellenistic world. Not myths, not metaphors, not artistic fantasies or poetic exaggerations. Actual physical machines, designed by named engineers, described in surviving texts, and in some cases confirmed by archaeological evidence. Machines that moved, that responded to stimuli, that performed complex sequences of actions, and that, in at least one verified instance, computed the positions of celestial bodies with a precision that would not be matched for over 1,000 years. The numbers are striking. Scholars have identified references to more than 80 distinct mechanical devices in surviving Greek and Roman texts, devices ranging from simple water clocks to programmable theatrical machines capable of executing multi-step performances lasting several minutes. Of these 80-plus devices, detailed construction plans survive for roughly 40. The rest are known only from descriptions, references, or fragments, and those 80 devices represent only the machines that someone bothered to write about, in texts that someone bothered to copy, in copies that survived the fires, floods, wars, and centuries of neglect that destroyed the vast majority of ancient literature. The true number of ancient automata built and operated in the Greek and Hellenistic world is, by any reasonable estimate, many times larger. Most are gone without a trace, no descriptions, no diagrams, no names, just absence. By the end of tonight, you are going to understand what these machines were, how they worked, who built them, and why their existence challenges nearly everything we think we know about the ancient world. You are going to learn about a tradition of mechanical engineering so advanced that it included programmable devices, feedback mechanisms, and binary logic systems, concepts that we associate with the computer age, but that were, in fact, first implemented in bronze and wood and pressurized water more than 2 millennia ago. And you are going to confront a question that has no comfortable answer. If the ancient Greeks could build robots, why did the Industrial Revolution take another 1,800 years? Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. To understand what the Greeks built, you first have to understand what they believed, because the story of Greek automata does not begin in a workshop, it begins in a poem. In the 18th book of the Iliad, the oldest surviving work of Western literature, composed sometime in the 8th or 7th century before the Common Era, the poet Homer describes the god Hephaestus at work in his divine forge. Hephaestus is the god of fire, metalwork, and craftsmanship, and his forge is not an ordinary smithy, it is a place of wonders. Homer describes golden handmaidens who attend the god, handmaidens made entirely of gold, who move, who speak, who think, and who possess intelligence and skill. They are not alive in the biological sense. They are made things, crafted things, artificial beings, endowed with the capacity for autonomous action. Homer calls them automata, the self-moving ones. It is the first known use of the word. But Homer does not stop there. In the same passage, he describes Hephaestus building a set of 20 tripods on golden wheels that move by themselves to the assembly of the gods and return on their own when the feast is over. These are self-navigating vehicles, robotic carts, if you will, described with a matter-of-factness that suggests Homer saw nothing particularly fantastic about the idea. The gods had technology. Technology could produce self-moving things. The concept was as natural to him as the concept of a chariot. What makes this passage so significant is not just its content, but its date. The Iliad was composed at the very dawn of Greek literary culture, at a time when the technology described in the poem was purely imaginary. No one in Homer's world could build a golden handmaiden or a self-moving tripod. These were fantasies, but they were specific fantasies, technological fantasies. Visions of a world in which craft skill could produce something indistinguishable from life. The Greeks did not merely dream of artificial beings in vague, mystical terms. They dreamed of them as engineering problems. And that distinction between a culture that imagines magical beings and a culture that imagines mechanical ones turns out to be profoundly important, because a culture that imagines mechanical beings is a culture that will eventually try to build them. And build them they did. The earliest physical evidence of Greek mechanical ingenuity comes not from automata, but from a related field, hydraulic engineering. By the 6th century before the Common Era, Greek engineers in the colonies of southern Italy and Sicily were constructing sophisticated water supply systems that used principles of siphoning, pressure regulation, and gravity-fed distribution that would not be improved upon for centuries. These were not automata in the dramatic sense. They did not move or perform, but they demonstrated a practical understanding of fluid mechanics that would later become the foundation of the automaton building tradition. The first named builder of mechanical devices in the Greek record is Archytas of Tarentum, a mathematician, philosopher, and statesman who lived in the first half of the 4th century before the Common Era. Archytas was a Pythagorean, a member of the philosophical school founded by Pythagoras, which held that the universe was fundamentally mathematical in nature, and that understanding its mathematical structure was the highest form of knowledge. This philosophical commitment to mathematical order drove Archytas toward mechanical experimentation because he saw machines as physical embodiments of mathematical principles, as proof that abstract relationships could be made real in wood and metal and moving parts. Archytas built what ancient sources describe as a wooden dove that could fly. The Roman author Aulus Gellius, writing in the 2nd century of the Common Era, describes the device in his Miscellany Attic Nights, a wooden figure in the shape of a dove, suspended by a mechanism of counterweights and pulleys, propelled by compressed air or steam, which could fly a certain distance before landing. The description is tantalizing and incomplete. Was this a true flying machine, a device that could sustain itself in the air? Or was it a powered projectile, launched from a mechanism and capable of gliding for a distance before falling? Modern engineers have debated this question extensively, and the consensus is that the latter interpretation is more likely. The dove was probably launched by a burst of compressed air and flew in an arc before landing. But even this conservative interpretation is remarkable. A self-propelled flying object, powered by compressed gas, built 400 years before the Common Era. The physics alone, the practical understanding of air pressure, gas expansion, and aerodynamic lift required to make such a device work, implies a level of engineering knowledge that has no obvious precedent in the Greek world, and Archytas was just the beginning. Within a century of his dove, the center of Greek mechanical innovation shifted from the Greek mainland and colonies to a new city that would become the undisputed capital of ancient engineering, Alexandria. Alexandria was founded by Alexander the Great in 331 before the Common Era, on the coast of Egypt at the western edge of the Nile Delta. From its inception, it was designed as a center of learning. Alexander's successors, the Ptolemaic dynasty, made the city the intellectual capital of the Hellenistic world by establishing two institutions that would transform the history of human knowledge: the Library of Alexandria and the Mausoleum, the Museum, a research institution attached to the library where scholars were supported by royal patronage to pursue knowledge in every field. The Mausoleum was not a museum in the modern sense. It was closer to a research university, a community of scholars funded by the state, working across disciplines, sharing ideas, and pushing the boundaries of what was known. It was in this environment, this unprecedented concentration of intellectual talent, financial support, and institutional continuity, that the Greek tradition of mechanical engineering reached its extraordinary peak. The Mausoleum attracted engineers, mathematicians, and inventors from across the Greek world, and it gave them something that no previous civilization had offered: the freedom and the funding to experiment systematically over long periods of time. The result was an explosion of mechanical innovation that lasted roughly 3 centuries, from the early 3rd century to the late 1st century before the Common Era, and that produced devices whose sophistication still astonishes modern engineers. The first great Alexandrian mechanician was Ctesibius, who flourished around 270 before the Common Era. Almost nothing is known of his personal life. His own writings are lost, completely, permanently lost, and he is known only through the descriptions and references of later authors, particularly Vitruvius and Hero. But those descriptions paint a picture of a mind of extraordinary ingenuity. Ctesibius invented the force pump, a device using pistons and valves to move water under pressure. He invented the water organ, the hydraulis, a keyboard-operated musical instrument in which air was compressed by water pressure and directed through pipes of different lengths to produce different tones. The water organ was the first keyboard instrument in history, the ancestor of every pipe organ, every harpsichord, and every piano that has ever been built. Ctesibius also dramatically improved the water clock, the clepsydra, transforming it from a simple draining vessel into a precision timekeeping instrument with a constant flow regulator, a float mechanism, and a pointer that moved along a calibrated scale. His improved water clock was the most accurate timekeeping device in the world for roughly 1,500 years, until the development of the mechanical escapement clock in medieval Europe. The water organ alone would have been enough to secure Ctesibius's place in the history of technology. But the instrument reveals something deeper about the Alexandrian engineering tradition: its interdisciplinary ambition. Ctesibius did not build the hydraulis because he wanted to play music. He built it because he wanted to understand air pressure, and he realized that a musical instrument offered the most precise and immediately audible way to demonstrate and test his pneumatic theories. Each pipe of the organ was a laboratory instrument as well as a musical one. The pitch of the note told Ctesibius whether the air pressure was correct. The consistency of the tone told him whether the pressure was stable. The speed of the response told him whether the valves were working efficiently. He was using sound as a measurement tool, converting invisible pneumatic phenomena into audible data that his ears could process with the same precision that a modern engineer uses digital readouts. This was not primitive tinkering. This was systematic experimental investigation, conducted through the medium of a musical instrument in a city where royal funding allowed a brilliant mind to spend years pursuing questions that had no immediate practical application. The culture of the Mausoleum encouraged this kind of cross-disciplinary exploration. Engineers worked alongside mathematicians, astronomers, physicians, and natural philosophers. The result was a tradition in which mechanical devices were not merely practical tools but philosophical instruments, physical demonstrations of abstract principles. This fusion of theory and practice, of mathematical reasoning and mechanical construction, was the engine that drove the Alexandrian tradition to heights that no purely practical or purely theoretical approach could have reached. It was, in a real sense, the first research and development culture in human history. But Ctesibius's most relevant contribution to the story of automata was theoretical rather than practical. He was, by all surviving accounts, the first person to develop a systematic understanding of pneumatics, the science of compressed air and its mechanical applications. He understood that air could be compressed, that compressed air could exert force, that this force could be used to move objects, and that the movement could be controlled by valves and regulators. This theoretical framework, primitive by modern standards but revolutionary in its time, became the foundation upon which every subsequent Greek automaton was built. Compressed air, pressurized water, gravity, and counterweights. These were the four forces that powered the ancient robots, and Ctesibius was the man who first understood how to harness them systematically. The tragedy is that we know all of this secondhand. Ctesibius wrote treatises describing his inventions and their principles. Those treatises were available to later engineers. Hero cites them repeatedly, but no copy survived the destruction of the ancient libraries. We know what Ctesibius built. We know how his machines influenced subsequent engineers. But we do not know, in his own words, how he thought about them. His intellectual framework, the conceptual architecture behind his machines, is gone. What remains is the equivalent of knowing that a great novel once existed, knowing its plot summary, and knowing its influence on later writers, but never being able to read a single sentence. No copies survive. The loss is permanent. After Ctesibius came Philo of Byzantium, who flourished around 200 before the Common Era. Philo was both an engineer and a writer, and unlike Ctesibius, fragments of his work have survived. His Mechanic Syntaxis, a multi-volume treatise on mechanical engineering, covered everything from siege engines to harbour construction to pneumatic devices. The surviving sections on pneumatics describe a series of ingenious devices, many of which qualify as automata in the truest sense, machines that perform actions without continuous human input. One of Philo's most celebrated devices was a mechanical servant, a figure of a woman holding a jug, who poured wine when a cup was placed in her outstretched hand. The mechanism worked through a clever combination of air pressure and gravity. The figure was hollow, and the jug was connected to an internal reservoir. When the cup, which had a specific weight, was placed on the figure's hand, the hand descended slightly under the weight, opening a valve that allowed wine to flow from the reservoir through the jug and into the cup. When the cup was filled and its weight increased further, a second mechanism triggered, closing the valve and stopping the flow. Remove the cup, and the hand returned to its original position, ready for the next guest. This is not a simple trick. This is a feedback mechanism, a device that senses an input, responds to it, and adjusts its behavior based on the result. The mechanical servant detects the presence of the cup through weight, dispenses a measured amount of wine, detects when the cup is full through the change in weight, and stops. It is, in the language of modern control theory, a closed-loop system, and it was built more than 2,200 years ago. Philo's mechanical servant is not just an engineering curiosity. It is a philosophical provocation. The device performs a task that, in the ancient world, was normally performed by a human slave, serving wine at a banquet. It does so autonomously, without human intervention, responding to stimuli in its environment and adjusting its behavior accordingly. The implications were not lost on ancient observers. If a machine could serve wine, what else could a machine do? If a bronze figure could sense the weight of a cup and respond appropriately, where was the boundary between the mechanical and the human? These questions, which we associate with modern artificial intelligence research, were being asked and being provoked by working machines more than 2 millennia ago. The ancient philosopher Aristotle, writing a century before Philo, had already imagined the social consequences of automation. In a passage from the Politics, he wrote that if every instrument could accomplish its own work, if the shuttle could weave and the plectrum could play the lyre by itself, then chief workmen would not want servants, nor masters' slaves. It is one of the most prescient statements in the history of technology, a recognition that automation could transform not just production, but the entire structure of society. Aristotle wrote this as a hypothetical, an if-then proposition about a future that he considered impossible. Within a century, Philo's mechanical servant had made the hypothetical concrete. The machine could serve. The question was whether anyone would let it. Philo also described a device that modern scholars have termed an automaton theatre, a miniature stage on which mechanical figures performed a dramatic sequence. The figures were mounted on a platform and moved by a system of strings, pulleys, and falling weights, with the timing of each movement controlled by the rate at which a weight descended through a regulated mechanism. The concept is identical in principle to a music box, a player piano, or a punched card programmed mechanical loom, a stored sequence of instructions executed automatically by a machine without human intervention. This is, by any reasonable definition, a programmable device. The program was physical, encoded in the arrangement of strings and the calibration of weights, but the concept is the same as the software that runs on a modern computer. A predetermined sequence of operations, stored in a medium, executed by a machine. The implications of this are staggering. Programming, the concept of storing a sequence of instructions and having a machine execute them, is not a 20th century invention. It is not an 18th century invention. It is a Hellenistic invention, developed in the workshops of Alexandria at least 2 centuries before the Common Era. But it was Hero of Alexandria, working roughly 3 centuries after Ctesibius, who brought all of these threads together into the most complete and sophisticated body of mechanical engineering to survive from the ancient world. Hero flourished in the 1st century of the Common Era. The exact dates are disputed, but most scholars place his major works between roughly 50 and 70 of the Common Era. He was a mathematician, an engineer, a teacher, and a prolific author, and the range and sophistication of his mechanical creations beggars belief. Hero's surviving works include the Pneumatica, a 2-volume treatise describing more than 75 pneumatic and hydraulic devices, the Automatopoietic, a manual specifically devoted to the construction of automata for theatrical performances, the Mechanica, a treatise on the principles of simple machines, the Dioptra, a work on surveying and measurement, and several other texts on mathematics, optics, and applied science. Taken together, these works constitute the most detailed surviving record of ancient engineering practice, a window into a world of mechanical sophistication that, without Hero's texts, we would scarcely believe had existed. The Automata Poieticae, the work on theatre automata, deserves particular attention because it describes something that sounds impossible: a fully automated theatrical production. Hero's automated theatre was a mobile platform, approximately 1.5 meters tall, that rolled out on its own from behind a screen, stopped at the center of the performance area, and then presented a dramatic performance in which miniature figures moved, scene changes occurred, sounds were produced, and special effects, including simulated lightning and fire, were deployed, all without any human operator touching the machine during the performance. When the show ended, the platform rolled back behind the screen on its own. The mechanism that powered this device was a large lead weight suspended above a container of grain or sand. As the grain slowly drained out of the container through a regulated opening, the weight descended at a controlled rate, pulling a network of strings and cords that were wrapped around axles, threaded through pulleys, and attached to the various moving parts of the theatre. Each cord was calibrated to activate at a specific point in the weight's descent, producing a precisely timed sequence of movements, scene changes, and sound effects. The rate of the weight's descent, and therefore the timing of the entire performance, was controlled by the size of the opening through which the grain drained. Hero describes how to adjust this opening to speed up or slow down the show. Read that again. A falling weight, regulated by a controlled flow of granular material, drives a timed sequence of mechanical events through a network of cords and pulleys. This is a program running on hardware. The falling weight is the power source. The draining grain is the clock. The network of cords is the instruction set. The mechanical figures, scenery, and sound effects are the outputs. The entire system is, in modern terms, a programmable, automated, timed sequence controller. the direct conceptual ancestor of every assembly line, every player piano, and every computer program that has ever existed. To grasp the sophistication of Hero's programming, consider the specific sequence he describes for one of his mobile theatre performances. A production dramatizing the myth of Nauplius, a hero of the Trojan War. The theatre rolls forward on its own. The doors swing open. The audience sees a tableau of Greek sailors repairing their ships after the fall of Troy. The figures of the sailors move, hammering, sawing, pulling ropes. The scene changes. The ships are now at sea. Miniature waves rise and fall. Dolphins leap through the water alongside the vessels. The scene changes again. A storm gathers. The figure of Athena appears above the scene. Lightning flashes, produced by a mechanism that rapidly rotates a painted panel behind a screen. One of the ships sinks. The figure of Nauplius appears on a promontory, holding a torch to lure the remaining ships onto the rocks. The ships crash. The doors close. The theatre rolls back behind the screen. All of this, the rolling, the opening, the multiple scene changes, the articulated figures, the waves, the dolphins, the lightning, the sinking ship, the closing, and the return, was executed automatically by the controlled descent of a single weight through a single regulated opening. Every movement was pre-programmed through the arrangement of chords and their attachment points on rotating axles. To change the performance, you change the chord arrangement exactly as a modern programmer changes the sequence of instructions in a computer program. Hero's automaton theatre was, in the most literal sense, a programmable machine. The only difference between Hero's technology and a modern computer is the medium in which the program is stored, chords and axles instead of magnetic storage or silicon chips. The concept is identical. Hero describes two types of automated theatres in the Automata Poeticae: mobile theatres that rolled on wheels, and stationary theatres whose doors opened automatically to reveal the performance. For both types, he provides detailed construction plans, including measurements, materials lists, and step-by-step assembly instructions. These are not vague descriptions. They are engineering blueprints. A competent modern engineer can, and several have, build working replicas directly from Hero's texts. But Hero's genius extended far beyond theatrical amusement. His Pneumatica describes devices of extraordinary ingenuity and variety. There are trick vessels that pour wine or water in unexpected ways. There are singing birds powered by water pressure. When water flows into a sealed chamber, the rising air pressure forces air through a whistle shaped like a bird's beak, producing a chirping sound. There are doors that open when a fire is lit on a nearby altar. The heat expands the air in a sealed vessel, pushing water into a bucket that descends under gravity and pulls the doors open through a rope and pulley mechanism. When the fire goes out, the air contracts, the water siphons back, the bucket rises, and the doors close. This last device, the automatic temple door, is worth pausing on. It uses thermal expansion of air to convert heat energy into mechanical work through the intermediary of water displacement. That is the operating principle of a steam engine. Hero also describes a separate device, the eolipile, a sealed sphere mounted on an axle with two bent nozzles on opposite sides, filled with water and heated over a flame. When the water boils, the steam escapes through the nozzles, and the reaction force spins the sphere on its axis. This is a steam-powered rotary engine, a working demonstration of the principle that would, 17 centuries later, power the Industrial Revolution. The fact that the ancient Greeks built a working steam engine and did not use it to power an industrial revolution is one of the most debated questions in the history of technology, and we will return to it. For now, the relevant point is simply this: the mechanical knowledge existed, the engineering principles were understood, the devices were built, documented, and deployed. This is not speculation. This is not reconstruction from fragmentary evidence. Hero's texts survive. His blueprints can be read. His machines can be and have been built. And Hero, brilliant as he was not working alone. He was the culmination of a tradition. Behind him stood Ctesibius, whose pneumatic principles made the machines possible. Behind Ctesibius stood Archytas, whose flying dove first demonstrated the potential of compressed air propulsion. Behind them all stood a culture, a civilization-wide commitment to the idea that the natural world could be understood through mathematics, and reproduced through engineering. The Greeks did not stumble upon automata. They reasoned their way to them, step by logical step, across 3 centuries of sustained investigation, and then they stopped, not all at once, not in a single catastrophe, but slowly, over the centuries that followed Hero's death. The tradition contracted. The Minoan lost its funding. The library at Alexandria suffered successive disasters: fire, neglect, political upheaval. The Roman Empire, which had absorbed the Hellenistic world, valued Greek engineering for its military and architectural applications, but showed less interest in the theoretical tradition that had produced the automata. The workshops that had trained generations of Alexandrian engineers closed or were repurposed. The texts were copied less frequently. The chain of knowledge, master to student, engineer to apprentice, builder to builder, began to thin. By the 4th century of the Common Era, the tradition was effectively dead. The texts survived, in part, but the living knowledge of how to read them, how to translate their instructions into working machines, how to improvise and troubleshoot and adapt the designs to different materials and conditions, had evaporated along with the workshops that had sustained it. The blueprints remained. The builders were gone. What followed was a silence that lasted over 1,000 years, a silence in which the most mechanically sophisticated civilization the world had ever known was reduced to a handful of names in library catalogues, a few fragmentary texts in monastic collections, and a growing incredulous sense among later scholars that something extraordinary had once existed and then, inexplicably, vanished. The core problem with Greek automata is not that they existed. The evidence for their existence is overwhelming, textual, archaeological, and experimental. The core problem is what their existence implies. Because if the ancient Greeks could build programmable machines, feedback-controlled dispensers, steam-powered rotary engines, and coin-operated vending devices more than 2,000 years ago, then the comfortable story we tell ourselves about the history of technology, the story in which progress moves steadily forward from primitive to advanced, from simple to complex, from ancient to modern, is wrong. Not incomplete, wrong. The story of technological progress as a steady ascent is so deeply embedded in our culture that questioning it feels almost heretical. We learn it in school, we see it in museums, we absorb it from every documentary, every textbook, every timeline that arranges inventions in a neat chronological sequence from the wheel to the microchip. The implicit message is always the same. We are smarter now. We know more now. Our ancestors were clever, but they were limited by the tools and knowledge available to them. The arc of technology bends toward improvement. The Greek automata shatter this narrative. They demonstrate that ancient engineers possessed conceptual frameworks, feedback control, programmable sequencing, pneumatic power, steam propulsion, that would not be independently redeveloped in Europe for well over 1,000 years. The gap is not a matter of decades. It is a gap measured in millennia. And the question of why that gap exists, why the knowledge was lost, why it was not applied, why it did not trigger an industrial revolution in the ancient world, is one of the most important and most uncomfortable questions in the history of human civilization. To understand the scale of the problem, consider the Antikythera mechanism. In 1901, sponge divers off the coast of the Greek island of Antikythera pulled a corroded lump of bronze from the wreck of a Roman-era ship that had sunk sometime around 60 to 70 before the Common Era. The lump sat in the National Archaeological Museum in Athens for decades, largely ignored, before a series of investigations beginning in the 1950s revealed it to be the remains of a geared mechanical device of extraordinary complexity. The Antikythera mechanism contained at least 30 interlocking bronze gears, possibly as many as 37, arranged in a configuration that allowed the device to model the motions of the sun, the moon, and probably the 5 planets known to the ancient world. It could predict lunar and solar eclipses. It tracked the 4-year cycle of the Panhellenic Games. It modeled the irregular motion of the moon, including its variable speed along its elliptical orbit, using an ingenious pin-and-slot mechanism that converted uniform circular motion into variable, angular velocity. The level of miniaturization and precision in its gearwork is comparable to that of European clockwork from the 18th century, roughly 1800 years later. The historian of science Derek de Solla Price, who conducted the first serious study of the mechanism in the 1950s and 60s, described his reaction in terms that reveal the depth of the challenge it posed to conventional historical understanding. Finding a thing like this is like finding a jet plane in the tomb of King Tutankhamun, he wrote. The analogy was deliberate. The Antikythera mechanism did not merely exceed expectations for ancient technology. It existed in a completely different category, a category that, prior to its discovery, historians had not believed was populated by any ancient artifact. But here is the problem. The Antikythera mechanism was not built by a lone genius working in isolation. It was a manufactured product. Its gears were cut with a regularity that implies the use of specialized tools and standardized techniques. This means that there must have been a tradition of precision gear cutting in the ancient world. Workshops that produced gears, tools that cut them, engineers who designed them, and a knowledge base that sustained the entire enterprise. None of this survives. No other ancient geared device of comparable complexity has ever been found. No ancient text describes the gear cutting techniques required to produce the mechanism's components. No workshop has been identified. The Antikythera mechanism is a single, solitary artifact, a message in a bottle from a civilization that possessed an entire technology of precision mechanics that has otherwise vanished without a trace. The most recent analysis of the mechanism, conducted using advanced X-ray computed tomography by a team led by the astronomer Mike Edmonds and the mathematician Tony Freeth, has revealed additional layers of complexity that earlier studies had missed. The mechanism modeled not just the Sun and Moon, but also the orbital periods of all 5 planets visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. It incorporated a sophisticated dial system on its rear face that predicted eclipses based on the Saros cycle, a period of approximately 18 years and 11 days after which the pattern of lunar and solar eclipses repeats. The inscriptions on the mechanism's surface, revealed by the X-ray scans, include operating instructions and astronomical data that show the device's creator possessed a detailed knowledge of astronomical theory, comparable to the best work of Hipparchus, the greatest astronomer of the ancient world. The gear ratios used in the mechanism are not simple whole number ratios. They include ratios like 223 to 127, complex fractions that precisely encode the known astronomical periods. Cutting gears with these specific tooth counts required not just precision metalworking, but also the mathematical ability to calculate the correct ratios from astronomical observations. The mechanism is, in other words, not just a machine. It is a physical embodiment of advanced mathematical astronomy, a computer, in the most literal sense, that takes astronomical inputs and computes predictive outputs through a mechanical process. Freeth and his colleagues have estimated that the mechanism required several years of skilled labor to construct using techniques, including the cutting of triangular toothed gears with module sizes below 0.5 millimeter, that push the limits of what is achievable with hand tools and visual inspection. The fact that such a device was built on a ship, apparently as a navigational or calendrical instrument for practical use, implies that it was not unique. Nobody builds a Rolls-Royce if no one has ever built a car. The Antikythera mechanism presupposes a prior history of simpler geared devices, a tradition of gear-cutting craftsmanship, and a community of practitioners who could produce, maintain, and use such instruments. All of that is gone, and it gets worse. The Antikythera mechanism is not the only category of ancient machine for which we have physical evidence but no surviving context. Consider the Baghdad battery, a clay jar, roughly 14 centimeters tall, containing a copper cylinder and an iron rod, sealed with bitumen, found in the ruins of a Parthian-era settlement near Baghdad, and dating to roughly the 1st or 2nd century of the Common Era. When filled with an acidic solution, vinegar for example, or citric acid, the device produces a small but measurable electric voltage, approximately 1.5 volts. The device's exact purpose remains debated. Electroplating, medical applications, and ritual uses have all been proposed, but its ability to generate electricity is not in question. Modern replicas work exactly as predicted, an electrochemical cell producing electricity from a chemical reaction built in the ancient Near East. The technology required to produce electricity was available more than a millennium before Alessandro Volta built his famous voltaic pile in 1800. And once again, there is no context, no surviving text that describes the device, no evidence of a broader tradition of electrochemistry, no indication that the principle was understood or developed further. Just a single artifact, sitting in a museum, quietly contradicting everything we thought we knew about the history of electrical science. The pattern is consistent and deeply troubling. Across the ancient world, we find evidence of technological capabilities that appear, flourish briefly or in isolation, and then vanish, leaving behind artifacts that modern science can analyze but cannot contextualize. The Greek automata fit this pattern perfectly. The texts that describe them survive. The engineering principles they employ are clear. Working replicas have been built, and yet the tradition that produced them, the workshops, the tools, the training methods, the accumulated practical knowledge of generations of engineers, is gone as completely as if it had never existed. The reasons for this disappearance are multiple and interrelated, and understanding them requires looking beyond the machines themselves to the civilization that produced them. The first reason is economic. The Greek and Hellenistic world was a slave economy. Labor was cheap, in many contexts, essentially free. The economic incentive to develop labor-saving machines, the incentive that would eventually drive the Industrial Revolution in 18th century Britain, was largely absent. Hero's steam engine, the eolipile, is the most cited example of this problem. The device demonstrates the principle of converting heat energy into rotary motion. In theory, it could power a pump, drive a mill, or turn a lathe. In practice, it was used as a novelty, a philosophical demonstration, a temple wonder, a toy. The technology existed. The economic motivation to develop it did not. The historian of ancient technology MJT. Lewis has pushed back against this explanation, arguing that the real barrier was not economic motivation but metallurgical limitation. A practical steam engine requires pressure vessels that can withstand sustained high pressures without rupturing, a capability that depends on the quality of the available metals, the precision of the seals, and the consistency of the manufacturing process. Ancient bronze smiths, Lewis argues, could produce vessels adequate for heroes' demonstrations but not for sustained industrial use. The pressures involved in a working power engine would have exceeded the capacity of ancient metallurgy. The knowledge existed, the materials did not. This argument has merit, but it does not fully resolve the puzzle. Even if a full-scale steam engine was beyond ancient metallurgical capabilities, the underlying principles, the relationship between heat, pressure, and mechanical work, could have been explored and documented in ways that would have preserved them for a future era with better materials. The fact that they were not explored systematically, that the eolipile remained a curiosity rather than becoming the subject of sustained investigation, suggests that the problem was not purely material but also intellectual and cultural. The ancient world lacked not only the metal for a steam engine, but also the intellectual framework that would have identified a steam engine as a worthy goal. The concept of harnessing natural forces for productive labor, the concept that drove the Industrial Revolution, was simply not part of the ancient worldview. Nature was something to be contemplated, not exploited. Machines were amusements, not servants. The idea that technology could fundamentally transform society, that the right machine could change everything, was not an idea that the ancient world possessed, or rather, it was an idea that some individuals possessed, but that the culture as a whole did not embrace. Hero himself, in the introduction to his Pneumatica, makes a remarkable statement that the study of pneumatics is valuable not only for its theoretical insights, but for its practical applications. He describes his devices as useful for temples, for public entertainment, for household convenience. This suggests that Hero, at least, understood the practical potential of his work, but his vision did not become a cultural program. No Hellenistic government embarked on a project to mechanize agriculture or manufacturing. No philosopher developed a theory of technological progress. The machines remained what they had always been: wonders. Beautiful, ingenious, awe-inspiring wonders, and nothing more. This explanation, while partially valid, is also too simple. The absence of economic motivation explains why certain technologies were not developed further, but it does not explain why they were lost. A technology that exists but is not widely adopted can still be preserved, in texts, in workshops, in the memories of practitioners. The Greek automata were not merely unadopted, they were forgotten. The knowledge of how to build them disappeared even from the written record for centuries. This requires a different explanation. The second reason is institutional. The Alexandrian tradition of mechanical engineering was sustained to a remarkable degree by a single institution, the Mausion and its associated library. The Ptolemaic kings funded the Mausion. The Mausion housed the engineers. The library preserved their texts. When Ptolemaic rule ended, when Egypt was absorbed into the Roman Empire after the Battle of Actium in 31 before the Common Era, the institutional support for systematic mechanical research began to erode. The Romans were pragmatic engineers, magnificent builders of roads, aqueducts, and public buildings, but they were not systematic researchers. They used technology. They did not theorize about it. The Roman intellectual tradition valued rhetoric, law, and philosophy. Engineering was a practical trade, not an intellectual discipline. Under Roman rule, the Mausion continued to function but gradually lost its status as a center of original research. The engineers, who had once been supported by royal patronage, now had to find practical applications for their skills, or find other employment. The third reason, and perhaps the most important, is the nature of the knowledge itself. Greek mechanical engineering was, like the ancient pigment traditions discussed in other contexts, a form of embodied knowledge, knowledge that lived in the hands and minds of practitioners, and that could not be fully captured in text. Heroes' treatises are remarkably detailed by ancient standards. They include measurements, materials lists, and step-by-step instructions. But anyone who has ever tried to build something from written instructions alone knows that written instructions are never enough. There are always gaps, moments where the text says, "attach firmly," without specifying exactly how, or "adjust until the mechanism operates smoothly," without explaining what smoothly means in practice. These gaps are filled, in a living tradition, by the tacit knowledge of the practitioner, the feel of the mechanism, the sound of the properly tensioned cord, the sight of the correctly aligned gear. When the living tradition dies, the gaps become chasms. The text remains. The ability to execute it does not. The destruction of the Library of Alexandria, which occurred not in a single catastrophic event, but through a series of partial destructions spread over centuries, eliminated much of the textual record. But even the texts that survived would have been insufficient to reconstruct the tradition, because the tradition was never fully textual. It was a living practice, sustained by living practitioners, and when those practitioners died without successors, the practice died with them. The fourth reason is cultural. The Greek and Roman intellectual elite regarded manual labor, including the labor of building machines, with varying degrees of condescension. Plutarch, writing in the 1st century of the Common Era, records that Archimedes, the greatest mathematician and engineer of antiquity, considered his mechanical inventions to be mere accessories of a geometry practiced for amusement, and refused to leave any written record of his engineering methods, regarding them as ignoble and sordid. If this attitude was widespread, and there is considerable evidence that it was, then the social prestige of mechanical engineering in the ancient world was far lower than its intellectual sophistication warranted. The engineers were brilliant. The culture did not always value their brilliance, and a skill that is not valued is a skill that is not preserved. This cultural disdain for manual and mechanical work had direct consequences for the preservation of engineering knowledge. When a Roman aristocrat compiled a library, he collected works of philosophy, rhetoric, poetry, and history. He did not collect engineering manuals. When a monastic scriptorium selected texts for copying, the process by which virtually all ancient literature was preserved through the medieval period. The monks chose works of theology, classical literature, and natural philosophy. They did not choose the treatises of Ctesibius or the workshop manuals of unnamed Alexandrian engineers. The survival of Hero's texts is, in this context, almost miraculous, a statistical anomaly, preserved partly because his mathematical content gave his work a veneer of philosophical respectability, and partly because his automata were entertaining enough to be considered worth reading as curiosities. But for every text of Hero's that survived, dozens of engineering treatises by his predecessors and contemporaries were lost, discarded, not copied, allowed to decay on forgotten shelves in libraries that no one maintained. The historian of ancient technology, Serafina Cuomo, has documented the systematic bias in ancient text preservation that favored theoretical over practical knowledge. In her analysis, the survival rate of ancient philosophical texts is roughly 10 to 15 times higher than the survival rate of ancient technical texts, not because technical texts were produced in smaller numbers, but because they were considered less worthy of the effort and expense of copying. This bias is not neutral. It has shaped our entire understanding of the ancient world. We know ancient Greece as a civilization of philosophers, poets, and politicians because those are the texts that survived. We do not know it as a civilization of engineers, mechanics, and builders because those texts were allowed to perish. Our image of ancient Greece is a product of medieval editorial choices, not of ancient reality. These four factors, economic, institutional, epistemic, and cultural, combined to create the conditions for one of the most profound technological losses in human history. The Greeks built machines that would not be matched for over 1,000 years, and then they forgot how. Not because the machines did not work, not because the principles were flawed, not because a conquering army deliberately destroyed the knowledge, but because the complex web of conditions that had sustained the tradition, royal patronage, institutional support, cultural prestige, economic motivation, and the living chain of master-to-apprentice transmission, unraveled, slowly and irreversibly, over the centuries following the Roman absorption of the Hellenistic world. By the 6th century of the Common Era, the tradition was a ghost. The texts were scattered across monastic libraries and private collections, rarely copied, poorly understood, and in many cases attributed to the wrong authors or confused with works of fiction. Hero's Pneumatica survived, but in copies that had been degraded by centuries of transmission, corrupted by scribal errors, missing diagrams, and the accumulated confusion of copyists who did not understand what they were copying. The mechanical knowledge that would have allowed a reader to fill in the gaps, to look at a diagram and understand how it should work, to read an instruction and know what the text was trying to convey, was gone. And here is what makes this truly terrifying. The knowledge almost survived. On at least 3 occasions in the centuries following the fall of Rome, the tradition of Greek mechanical engineering came within reach of revival, and each time the revival failed. The first was in the Islamic world. During the Great Translation movement of the 8th and 9th centuries, Arab scholars translated many of Hero's and Philo's works into Arabic, and Islamic engineers built on this foundation to create their own magnificent tradition of automata. The Banu Musa brothers, 3 scholars working in 9th century Baghdad named Muhammad, Ahmad, and Al-Hassan, wrote the Kitab al-Hiyal, the Book of Ingenious Devices, which described over 100 mechanical devices, many directly inspired by Greek originals. Their treatise demonstrates both deep engagement with the Greek sources and significant original innovation. Several of their devices, including trick-drinking vessels, self-trimming lamps, and an automated flute player, go beyond anything described in surviving Greek texts, suggesting either that the Banu Musa had access to Greek sources that are now lost to us, or that they had developed their own engineering insights that extended the Greek tradition in new directions. The engineer Al-Jazari, working in the Artukid court in Diyarbakir in the late 12th and early 13th centuries, represents the peak of the Islamic automaton tradition. His treatise, The Book of Knowledge of Ingenious Mechanical Devices, completed in 1206, describes 50 devices of remarkable sophistication. His most famous creation was an elaborate water clock in the form of an elephant carrying a castle, in which a system of floats, pulleys, and counterweights drove a sequence of automated figures that marked the passage of each half hour. The clock included a scribe who rotated to point at the current time, a bird that chirped and tilted, and a mahout who struck the elephant with a stick at each interval. The entire device was powered by water and required no external intervention to operate. Al-Jazari also built what many historians consider to be the first programmable automaton in the Islamic tradition, a boat carrying 4 mechanical musicians who could be programmed to play different rhythmic patterns by adjusting the position of pegs on a rotating drum. The drum functioned exactly as a music box cylinder or a punched card, a physical medium storing a sequence of instructions that the machine read and executed. The concept was the same as Hero's automated theatre, but applied to music rather than drama. But the Islamic tradition, while brilliant in its own right, was working from translated and incomplete Greek sources. The original context, the workshop practice, the engineering culture, the accumulated tacit knowledge was already gone. The Arab engineers were rebuilding from blueprints, not from living tradition. And their own tradition, in turn, was disrupted by the Mongol invasions, the political fragmentation of the Islamic world, and the same forces of economic change and institutional decline that had destroyed the Greek original. The second near revival came in the European Renaissance, when Hero's texts were rediscovered and translated into Latin and then into vernacular languages. Engineers across Europe were fascinated by the descriptions of ancient automata, and many attempted to build replicas. Some succeeded. Leonardo da Vinci, who was deeply influenced by classical mechanical texts, designed and possibly built a mechanical knight, a programmable drum machine, and various other automata. But the Renaissance engineers, like their Islamic predecessors, were working from texts, not from tradition. They could read what Hero described. They could not feel what Hero's craftsmen felt. The gap between text and practice, once again, proved impossible to close. The third near revival came in the 17th and 18th centuries, when the development of clockwork technology in Europe finally produced a mechanical tradition sophisticated enough to match, and in some cases exceed, the achievements of the ancient Greeks. The automata of Jacques de Vaucanson, Pierre-Jacques Droz, and other European clockwork masters were marvels of mechanical engineering. A mechanical duck that ate and digested food, a writing boy that dipped a pen in ink and wrote actual letters on paper, a musician that played a flute with the correct fingering and embouchure. These machines were in many ways more sophisticated than their Greek predecessors, but they were independent inventions, products of a European mechanical tradition that had developed separately over centuries, without direct continuity with the ancient Greek tradition. The Greek achievement had been duplicated, not recovered. The original knowledge remained lost, and so the pattern completes itself. A tradition of extraordinary mechanical sophistication, developed over 3 centuries in the workshops of the Hellenistic world, vanished into the gap between written text and living practice. It was almost recovered by the Arabs. It was almost recovered by the Renaissance. It was eventually surpassed by the European clockwork tradition, but it was never truly restored. The specific knowledge of the Greek engineers, their materials, their methods, their shortcuts, their tricks, their accumulated wisdom about what works and what does not, is gone. What survives is the outline preserved in Hero's texts and their translations. The substance, the embodied, practical, lived knowledge of the tradition, is dust. The real question is not what burned, it is what we will never know existed. Hero's texts describe roughly 75 to 80 devices. How many more were built that Hero did not describe? How many were invented by engineers whose names and works are entirely lost? How many represented dead ends, experiments, prototypes, improvements that were tried and discarded or tried and forgotten? The devices we know about are the survivors of a process of textual selection that favoured the impressive and the well-documented. Behind them lies an unknowable number of machines that were built, used and lost without a trace. The dark matter of ancient technology, invisible but almost certainly vast. The scale of what was lost becomes clearer when we examine the few surviving references to engineers and texts that did not survive. Ctesibius alone is credited with inventions spanning at least 3 distinct categories of mechanical engineering: pneumatics, hydraulics, and precision measurement. His works were cited by at least 4 later authors, yet not a single page of his writing survives. Philo of Byzantium wrote a multi-volume encyclopedia of mechanical engineering, the Mechanic Syntaxis, of which only fragments survive, mostly in Arabic translation. The original Greek text of even these fragments is lost. The Roman architect Vitruvius, writing in the 1st century before the Common Era, references at least a dozen Greek mechanical engineers by name: Archimedes, Ctesibius, Philo, Diades, Charius, Polyidus, and others, many of whom wrote treatises that Vitruvius clearly had access to, but that have since perished entirely. For these engineers, we do not even have fragments. We have only their names and the briefest summaries of their achievements, filtered through the sensibility of a Roman writer who was interested in practical applications rather than theoretical principles. Vitruvius himself provides a telling example of the gap between what was known and what survived. In the 10th book of his De Architectura, he describes a range of machines: cranes, water-lifting devices, siege engines, water organs, and odometers, with enough technical detail to demonstrate that he was drawing on a rich tradition of engineering literature. But his descriptions are selective and simplified. He is writing for Roman builders, not for engineers. He includes what they need to know and omits the deeper theoretical framework. The result is a text that preserves the surface of ancient engineering knowledge while the depths are lost. The case of Archimedes is perhaps the most painful of all. Archimedes of Syracuse, who lived in the 3rd century before the Common Era, is universally regarded as one of the greatest mathematical and engineering minds in human history. His mathematical works on the areas and volumes of geometric figures, on the properties of spirals, on the principles of buoyancy and leverage, survive in sufficient quantity to confirm his genius. But his engineering works are almost entirely lost. Plutarch tells us that Archimedes built extraordinary machines for the defense of Syracuse during the Roman siege of 212 to 210 before the Common Era, cranes that could lift and overturn enemy ships, catapults of unprecedented power and accuracy, and possibly a system of mirrors that focus sunlight to ignite enemy vessels. But Archimedes himself, according to Plutarch, refused to write about his mechanical inventions. The greatest engineer of the ancient world considered engineering unworthy of permanent record. If Archimedes, whose mathematical works were copied, recopied, and treasured for millennia, refused to document his machines, how many lesser engineers also refused? How many brilliant devices were built by craftsmen who shared Archimedes' disdain for written documentation? The surviving texts are not a representative sample of ancient engineering. They are the thin upper layer of a tradition whose bulk lies hidden beneath the waterline of history, forever inaccessible. And it is here, in the contemplation of this invisible mass of lost knowledge, that the true weight of the loss becomes clear. The Greek automata that we know about, Hero's theatres, Ctesibius's water organs, Philo's mechanical servants, the Antikythera mechanism, are dazzling. They represent achievements that modern engineers study with genuine admiration and, in some cases, genuine puzzlement. But they are the peaks of a mountain range whose lower slopes are entirely submerged. The tradition that produced them was broad, deep, and continuous over centuries. What survives is a handful of summits protruding above the surface of historical oblivion. The mountain itself, the vast infrastructure of workshops, tools, training, and accumulated practical knowledge that made the peaks possible, is gone. But here is what makes this truly terrifying. The knowledge did not die all at once. It died in stages, each stage removing a layer of capability that could never be restored. First went the institutional support, the royal patronage that funded the motion, the economic structures that sustained the workshops. Then went the practitioners, the engineers and craftsmen who carried the tacit knowledge in their hands and their habits. Then went the texts, not in a single burning but through the slow attrition of neglect, as copies deteriorated and were not replaced. Then went the context, the understanding of what the surviving text meant, as later readers lacked the practical background to interpret technical descriptions. And finally went the memory, the awareness that the tradition had ever existed. As the centuries accumulated and the ancient world receded into myth and legend, by the time the Renaissance began to rediscover the texts of Hero and Philo, nearly everything had been lost except the words themselves. The words survived. The world that had given them meaning did not. And perhaps the most bitter irony of all is this. When the European engineering of the 18th and 19th centuries finally developed the technologies that the Greeks had glimpsed, steam engines, programmable machines, feedback mechanisms, automated manufacturing, they did so without any awareness that they were treading a path that had been walked before. James Watt did not know about Hero's eolipile. Joseph Marie Jacquard, who invented the programmable loom using punched cards in 1804, did not know about Hero's programmable theatre or Al-Jazari's programmable drum. Charles Babbage, who designed the first general-purpose mechanical computer in the 1830s, did not know about the computational sophistication of the Antikythera mechanism. Each of these innovators believed he was the first. Each was, in fact, the second, or the third, or the fourth, in a chain of invention whose earlier links had been broken and forgotten. We will never know how much faster modern technology would have developed if the Greek tradition had survived. The counterfactual is unanswerable. But the question haunts the history of technology like a ghost. What if they had not forgotten? What if the chain had not broken? What if the machines of Alexandria had been the beginning, not the end? The silence after those questions is the same silence that fell over the Minoan when the last engineer walked out of its doors. The surviving record of Greek automata contains specific devices whose engineering sophistication warrants close, individual attention, not as items on a list, but as investigations in their own right. Each one reveals a different dimension of what the ancient engineers achieved, and each one exposes a different facet of what we have lost. What follows are 5 such investigations. 5 ancient machines, each one a small world of ingenuity, mystery, and irrecoverable knowledge. The first is Hero's automatic temple doors. The device is described in detail in the Pneumatica, and it remains one of the most frequently cited examples of ancient engineering for good reason. It demonstrates, in a single mechanism, the ancient understanding of thermal expansion, pneumatic pressure, hydraulic transmission, and mechanical leverage. 4 fundamental principles of physics, combined in one device, for a purpose that was essentially theatrical. The mechanism worked as follows. An altar stood before a pair of closed temple doors. Within the altar was a sealed metal vessel, a sphere or cylinder connected by a pipe to a second vessel positioned beneath the floor. This second vessel was partially filled with water and was connected by chains or ropes to the door pivots. When a priest lit a fire on the altar, the heat expanded the air inside the sealed vessel. The expanding air pushed down through the pipe into the lower vessel, displacing the water. The displaced water flowed through a channel into a hanging bucket. As the bucket filled and grew heavier, it descended, pulling the chains that rotated the door pivots, and the temple doors swung majestically open, apparently of their own accord, apparently in response to the sacred fire. When the fire was extinguished, the process reversed. The air in the upper vessel cooled and contracted, creating a partial vacuum that sucked the water back from the bucket through the channel. The bucket lightened, rose, and the doors swung closed. The priests, presumably, did not explain the mechanism to the worshippers. The effect was designed to inspire awe, to create the appearance of divine agency, and it must have been effective. Imagine standing in a marble temple, watching a priest light a flame on the altar, and then seeing the massive bronze doors swing silently open as if pushed by an invisible hand. The moment would have been genuinely numinous, an encounter with what appeared to be supernatural power, but was, in fact, an encounter with engineering so sophisticated that it could simulate the supernatural. But the device's significance extends far beyond its theatrical application. The automatic temple doors represent a complete thermodynamic system, a system that converts heat energy into mechanical work through the intermediary of fluid displacement. The air is heated, it expands, it displaces water, the water's weight provides the motive force, and the force is transmitted to the doors through a mechanical linkage. This is, in principle, exactly what a steam engine does. The difference is one of scale, not of concept. Hero built a device that operated on the same fundamental principles as the machines that would power the Industrial Revolution, and he built it to open doors in a temple. Modern engineers who have built replicas of the automatic temple doors report that the device works reliably but slowly. The expansion and contraction of air are gradual processes, and the doors take several minutes to open or close. This slowness, which might seem like a limitation, was probably an advantage in the original context. Slow, ponderous movement added to the sense of gravitas and divine power. A door that snapped open instantly would look mechanical. A door that swung open gradually, as if moved by an unseen presence, would look miraculous. The question that the automatic temple doors raise, and that no surviving text answers, is how many temples in the ancient world were equipped with such mechanisms. Hero describes the device as though it were well known, not as though he were presenting a novelty. The implication is that automatic doors, or devices like them, were a standard feature of at least some ancient temples. If so, then the ancient world's experience of religion was, in some temples, mediated by engineering in ways that modern historians have only recently begun to appreciate. The gods spoke through machines, the divine acted through pneumatics, and the engineers who made the gods act were hidden behind the altar, invisible, unacknowledged, and ultimately forgotten. The relationship between ancient automata and religious practice deserves more attention than it typically receives, because it reveals a dimension of the tradition that purely technical discussions often miss. The automata were not just demonstrations of engineering skill. They were instruments of power, tools that allowed priests and rulers to manufacture the appearance of divine intervention. In a world where political authority was often grounded in religious legitimacy, the ability to make a god act, to open doors, pour libations, produce sounds, or move statues, was not a parlor trick. It was a political technology. The priest who could make a temple door open at the touch of a flame possessed a tool of persuasion more powerful than any argument or edict. He possessed a miracle on demand. Hero himself seems to have been aware of this dimension. In his Pneumatica, he describes several devices explicitly designed for use in temples, and his tone is consistently pragmatic. He describes them as useful instruments, not as philosophical demonstrations. One device produces the sound of a trumpet when a temple door opens. Another causes wine to flow from a statue's hand when a sacrifice is placed on an altar. A third makes a flame appear to light spontaneously on an altar when water is poured on it, using the chemical reaction between quicklime and water to generate heat. These are not mere toys. They are tools of religious theatre designed to produce specific emotional and psychological effects in worshippers. They are technologies of persuasion. The loss of these devices, and more importantly, of the knowledge of how to build them, did not merely deprive the world of clever machines. It deprived it of an entire category of understanding about the relationship between technology and social power. The ancient engineers understood something that we have only recently rediscovered, that machines are not neutral. They are instruments of influence, embedded in social and political contexts that determine their meaning and their impact. A machine that opens a door is neutral. A machine that opens a temple door, making worshippers believe that a god has acted, is a political and psychological instrument of the first order. The ancient engineers built both kinds. Modern histories tend to remember only the first. The second investigation concerns a device that does not survive in physical form, but whose description in Hero's texts has been confirmed by multiple modern replications: the programmable cart. Hero describes, in the Automata Poetique, a self-propelled cart, a platform on wheels that could move forward, stop, turn, reverse, and stop again, following a predetermined path without any human operator. The mechanism was powered by a falling weight, a heavy lead block attached to a cord that wound around the cart's axle. As the cord unwound, the axle turned and the cart moved forward. The speed was regulated by the same grain-draining mechanism used in the automaton theatre. The direction of movement was controlled by pins inserted into the axle at specific points. When the axle rotated to a pin, the pin engaged a steering mechanism that turned the front wheels, changing the cart's direction. By arranging the pins in different positions, the builder could program the cart to follow any desired path. Forward, turn left, straight, turn right, stop, reverse. This is, in the most literal and unambiguous sense, a programmable robot. It moves autonomously through space. Its path is determined by a stored program, the arrangement of pins on the axle. The program can be changed by rearranging the pins. The cart is a direct ancestor of every programmable mobile robot, every autonomous vehicle, every self-driving car that has ever been built or conceived. And it was described with full construction details in the 1st century of the Common Era. The roboticist Noel Sharkey of the University of Sheffield has built a working replica of Hero's programmable cart and confirmed that it operates exactly as described. Sharkey has written extensively about the implications of his replication, arguing that the cart represents a level of mechanical sophistication that was not equalled in Europe until the clockwork automata of the 18th century, a gap of roughly 1700 years. When I built Hero's cart and watched it follow its programmed path across my laboratory floor, Sharkey has said, I felt a chill, because I realized I was watching a machine that had been forgotten for almost 2 millennia, a machine that, if it had been developed further, could have changed everything. Sharkey's replication highlighted another aspect of the programmable cart that is easy to overlook, its modularity. The program, the arrangement of pins on the axle, was not fixed. It could be changed. Different pin arrangements produced different paths. This means the cart was not a single-purpose device, but a general-purpose platform, a machine that could be reprogrammed to perform a variety of tasks, simply by reconfiguring its physical instruction set. In modern terms, the cart's hardware was separated from its software. The hardware, the wheels, the axle, the weight, the steering mechanism, remained constant. The software, the pin arrangement, could be changed. This separation of hardware and software is one of the foundational concepts of modern computing. And here it is, implemented in bronze and wood, 2,000 years before Alan Turing formalized the idea mathematically. The programmable cart also demonstrates another principle that is fundamental to modern robotics: dead reckoning, the ability of a mobile device to navigate through space, based on internal measurements of its own motion rather than external reference points. The cart does not look where it is going. It has no sensors, no vision system, no environmental awareness. It simply executes its programmed sequence of movements and trusts that the starting position and the movement parameters will result in the desired path. This is exactly how early industrial robots operated, and, in some applications, how modern robots still operate. The principle is ancient, the implementation is ancient, only the recognition of its significance is modern. Hero's programmable cart raises one more question that deserves attention. The device was described in a treatise on automata for theatrical performances. Its purpose, in Hero's account, was to carry scenic elements on and off stage as part of an automated dramatic production. It was, in other words, a stage prop, a component of an entertainment system. The most sophisticated programmable mobile device in the ancient world was built for the theatre. This tells us something important about the social context of ancient engineering. The automata were, predominantly, entertainment technologies. They were built for temples, for banquets, for theatrical performances, for public displays. They were not built for production, for agriculture, for manufacturing, or for transportation. The engineering knowledge that could have transformed the ancient economy, that could have mechanized labor, increased productivity, and perhaps triggered something resembling an industrial revolution, was directed instead toward amusement and spectacle. The genius was real. The application was, from a modern perspective, breathtakingly narrow. Why? The answer returns us to the slave economy. In a world where human labor was abundant and cheap, there was no economic incentive to mechanize production. But there was enormous social incentive to produce spectacle, to impress, to entertain, to demonstrate the wealth and power of a patron through the display of marvels. The automata were products of a patronage system in which wealthy individuals and state institutions funded engineering projects not for economic return but for social prestige. The most impressive machine was not the most useful machine, but the most astonishing one. The machine that made spectators gasp, that made worshippers believe in divine intervention, that made dinner guests marvel at the ingenuity of their host. Engineering in the ancient world was, fundamentally, a performing art, and like all performing arts, it was ephemeral, brilliant in the moment, but leaving nothing behind when the performance ended and the audience went home. This observation raises one of the most tantalizing counterfactual questions in the history of technology. What if the ancient engineers had been embedded in a different economic system, one in which labor was expensive and mechanization was profitable? What if the patrons had demanded not spectacle, but productivity? What if the eolipile had been developed not as a temple wonder, but as a power source? The engineering knowledge was sufficient. The conceptual framework was in place. The missing ingredient was not intelligence or capability, but motivation, the specific kind of economic pressure that would have turned amusement into industry. The historian of economics, Moses Finley, argued that this counterfactual is essentially meaningless, that the ancient economy was structured in a way that made industrialization conceptually impossible, not just practically unlikely, in a society where wealth was measured in land and labor rather than in capital and productivity. The idea of using machines to replace human workers was not merely unattractive, it was unthinkable. The entire conceptual apparatus of industrial capitalism, investment, return on capital, labor productivity, economies of scale, did not exist. The machines existed. The framework that would have given them economic meaning did not. But Finley's argument, while influential, has been challenged by historians who point to specific ancient industries, mining, agriculture, textile production, where labor-saving technology was adopted when it was available and economically advantageous. The Archimedes screw, used for irrigation and mine drainage, was widely adopted precisely because it reduced the labor required for a specific task. The watermill, which appeared in the late Hellenistic period and spread throughout the Roman Empire, mechanized the grinding of grain, replacing one of the most labor-intensive tasks in the ancient economy with a machine that operated continuously with minimal human supervision. These examples suggest that the ancient world was not as economically hostile to mechanization as Finley argued. The barriers were real, but they were not absolute. Under the right conditions, ancient technology could and did find productive applications. The third investigation takes us from the workshop to the battlefield, and from the realm of confirmed devices to the shadowy borderland between historical record and engineering possibility. The so-called heat ray of Archimedes. The story, recorded by several ancient sources with varying degrees of detail and credibility, is this. During the Roman siege of Syracuse in 212 to 210 before the Common Era, Archimedes organized the defense of the city using a range of ingenious machines. Among these, according to the later accounts of Lucian, Galen, and the Byzantine historian John Tzetzes, was a system of mirrors or polished shields that could focus sunlight onto enemy ships, setting them on fire at a distance. The story has been debated for centuries. Is it physically possible? Could ancient mirrors focus enough solar energy to ignite a wooden ship? Modern experiments have produced mixed results. In 1973, the Greek engineer Ioannis Sakis conducted an experiment in which 70 flat bronze-coated mirrors, each approximately 1.5 meters by 1 meter, were positioned by Greek sailors and directed at a wooden boat at a distance of roughly 50 meters. The boat caught fire within minutes. The experiment demonstrated that the basic physics was sound, that a sufficiently large array of mirrors could, in fact, concentrate enough solar energy to ignite a wooden target at a meaningful distance. However, subsequent experiments, including a well-publicized attempt by the television program Mythbusters, have raised questions about the practicality of the device under combat conditions, moving ships, variable weather, the difficulty of coordinating dozens of mirror operators to maintain focus on a single point. All of these factors make the heat ray a questionable weapon. Most historians of technology now regard the story as probably exaggerated, likely based on a real defensive use of reflected sunlight, perhaps for dazzling or disorienting enemy sailors, that was inflated by later storytellers into a more dramatic weapon. But the story matters regardless of its literal truth, because it tells us something important about how the ancient world thought about its engineers. Archimedes was, in the ancient imagination, a figure of almost supernatural power, a man whose intellect could bend the physical world to his will. The heat ray story, whether literally true or not, reflects a cultural belief that engineering could achieve effects that seemed miraculous. In a world where temple doors opened by invisible forces and mechanical servants poured wine, the idea that a mathematician could set ships on fire with mirrors was not implausible. It was consistent with the general understanding that machines could do things that seemed impossible. The loss of the engineering tradition did not just deprive the world of specific machines. It deprived the world of a way of thinking, a conviction that the physical world was malleable, that nature's forces could be redirected and controlled, and that the right engineer, given the right tools, could achieve the seemingly impossible. That conviction would not return to the Western world for over 1,000 years. The story of the heat ray also illustrates a subtler point about how ancient engineering knowledge was transformed in the process of transmission. The original accounts of the siege of Syracuse, written by historians like Polybius, who lived close to the events, describe Archimedes' war machines in relatively sober terms: catapults of great range and accuracy, cranes that could overturn ships, and various other devices that exploited mechanical advantage with devastating effect. The mirror weapon does not appear in the earliest sources. It appears later, in accounts written centuries after the siege, when the memory of Archimedes had been inflated from historical genius to semi-mythical figure. The heat ray, in other words, may be a legend that grew from a kernel of truth, a story that became more dramatic with each retelling, as the details of what Archimedes actually built were forgotten and replaced by increasingly spectacular fantasies. This process, the inflation of legend as practical knowledge is lost, is a recurring pattern in the history of ancient technology. When the machines are no longer understood, the stories about them become magical. The gap between what the engineer actually achieved and what the storyteller claims he achieved widens with each generation until the real achievement, which was impressive enough, is buried under layers of mythologized exaggeration. Ironically, this inflation can actually accelerate the loss of real knowledge, because scholars who encounter the inflated legends dismiss them as fiction, and, in doing so, dismiss the genuine engineering achievements that the legends dimly preserve. The baby goes out with the bath water. The real machines are forgotten because the fake miracles are unbelievable. The fourth investigation returns to solid ground, to a device whose physical remains survive and whose engineering has been verified beyond dispute: the Lycurgus cup. The Lycurgus cup is a Roman glass vessel dating to the 4th century of the Common Era, now housed in the British Museum. It is made of dichroic glass that changes colour depending on how light interacts with it. When illuminated from the front, the cup appears an opaque jade green. When illuminated from behind, when light passes through the glass rather than reflecting off its surface, the cup becomes a translucent, glowing ruby red. The effect is startling, beautiful, and, until the 1990s, completely unexplained. Analysis using transmission electron microscopy revealed the secret. The glass contains tiny particles of gold and silver, roughly 70 nanometers in diameter, about 1,000 times smaller than the width of a human hair. These nanoparticles interact with light in a way predicted by a branch of physics called plasmonics. The oscillation of free electrons on the surface of the metal particles absorbs and scatters certain wavelengths of light, producing different colors depending on whether the light is reflected or transmitted. The Lycurgus cup is, in modern terminology, a nano-engineered optical material. The Romans who made it were working with nanotechnology, manipulating matter at the scale of billionths of a meter, roughly 1,700 years before the word nanotechnology was coined. But here is the problem. The Romans almost certainly did not understand what they were doing at the nanoscale. They could not see nanoparticles. They had no concept of electromagnetic radiation or electron oscillation. They achieved their result through empirical experimentation, through trial and error, through mixing different metals into their glass batches, and observing the results through a tradition of glassmaking craft that had, over generations, stumbled upon a combination that produced an extraordinary optical effect. And that tradition is gone. No Roman text describes how to make dichroic glass. No recipe survives. No workshop has been identified. The Lycurgus cup is one of only a handful of surviving Roman dichroic glass objects, and none of the others achieves the same quality. The cup represents the peak of a tradition whose lower slopes, the generations of experimentation, the failed batches, the incremental improvements, the accumulated understanding of how metal inclusions affect glass color, are entirely invisible. Modern materials scientists can now produce dichroic glass with nanoparticle inclusions. They do so using analytical chemistry and precision manufacturing, approaches completely different from the empirical craft-based approach of the Roman glassmakers. The Roman method, the specific sequence of steps that produced this specific result using the tools and materials available in the 4th century, is lost. We can explain the cup. We cannot replicate the journey that created it. The Lycurgus cup is technically not a Greek automaton. It is a Roman glass vessel, and it does not move or perform. But it belongs in this investigation because it demonstrates the same fundamental principle that underlies the entire automaton tradition. That ancient craftsmen achieved results at the frontier of material science through methods that were empirical, embodied, and ultimately unrecoverable. The cup is the static cousin of the automaton, a material achievement so advanced that it required 2,000 years of subsequent scientific development before its operating principles could be understood. If the Romans could accidentally produce a nano-engineered optical material, what could they have deliberately produced if they had understood what they were doing? The question, once again, is unanswerable. The tradition that could have developed that understanding was never given the chance to mature, and the Lycurgus cup raises another troubling possibility. If the Romans produced nanotechnology without understanding it, then how much other nanotechnology did ancient craftsmen produce? In glass, in metals, in ceramics, in pigments that we have not yet identified. The analytical tools required to detect nanoscale features in ancient materials, transmission electron microscopy, scanning probe microscopy, X-ray diffraction at nanometer resolution, have only been available for a few decades. The systematic examination of ancient artifacts with these tools has barely begun. Every year, new studies reveal nanoscale features in ancient materials that were previously undetected. The full picture of ancient nanoscale engineering is still emerging, and every new finding makes the picture more complex and more humbling. The 5th and final investigation brings us to the most enigmatic category of ancient automata, the ones that were designed not to perform tasks, but to think. In the 1st century before the Common Era, the Roman orator Cicero described a device built by Archimedes, a mechanical sphere that reproduced the motions of the sun, moon, and planets. Cicero claimed to have seen the device himself, and his description makes clear that it was not merely a static model, but a working mechanism, a machine that could be operated to display the positions of the celestial bodies at any given time. If Cicero's account is accurate, then Archimedes built a planetarium, a mechanical computer that modeled the solar system, roughly a century before the Antikythera mechanism was constructed. Cicero's description raises the possibility that the Antikythera mechanism was not a unique artifact, but a member of a class. One example of a broader tradition of mechanical astronomical computers that was widespread enough to be familiar to educated Romans. If so, then the loss is not of a single device, but of an entire category of technology. The mechanical computation of astronomical predictions. This category would not be reinvented in Europe until the development of the astronomical clock in the 14th century. A gap of roughly 1,500 years. The math is striking. 1,500 years of computational capability vanished. 1,500 years during which every astronomer who wanted to predict an eclipse or track a planetary orbit had to do so by hand calculation. Laborious, error-prone, time-consuming hand calculation, because the machines that could have done it for them had been built, used, and forgotten. The astronomer and historian of science James Evans has written about this loss with a precision that captures its full weight. The Antikythera mechanism, Evans has observed, is not just a marvel of ancient engineering, it is evidence of an entire tradition of mechanical computation that we did not know existed. It forces us to ask, what else existed that we do not know about? What other traditions of mechanical ingenuity flourished in the ancient world, produced working devices, and then disappeared completely? The mechanism is a window, but the room it opens onto is dark. That darkness, the unknowable vastness of what was built and lost, is the true legacy of the Greek automaton tradition. The 5 devices examined here, the automatic temple doors, the programmable cart, the Archimedean heat ray, the Lycurgus cup, and the mechanical planetaria, represent 5 different facets of a tradition whose full scope we can only guess at. Each one is extraordinary in its own right. Together, they outline the shape of something even more extraordinary, a civilization that had begun to mechanize its relationship with the physical world, that had developed the conceptual tools for automation, computation, and feedback control, and that then, for reasons that are understandable but no less tragic for being understandable, let those tools slip through its fingers. These 5 investigations share a common lesson. In each case, modern science has confirmed the reality of the ancient achievement. In each case, modern engineers have struggled to replicate it fully without access to the tacit embodied knowledge of the original builders. And in each case, the gap between what we can analyze and what we can reproduce reveals the same uncomfortable truth, that the ancient world knew things we do not know in ways that our civilization is not equipped to recover. The knowledge was not inferior to ours, it was different from ours. And the difference, the gap between analytical knowledge and craft knowledge, between knowing what and knowing how, is the space in which the Greek automaton tradition lived, flourished, and died. There is a moment that every historian of ancient technology encounters sooner or later, a moment of vertigo, when the accumulation of evidence shifts from interesting to unsettling. It is the moment when you stop thinking of the Greek automata as isolated achievements and start seeing them as symptoms, as the visible tips of a technological iceberg whose submerged mass you can sense but never fully perceive. The surviving record names perhaps a dozen ancient engineers. Behind those names lie hundreds, probably thousands, of unnamed practitioners, the craftsmen who cut the gears, the smiths who forged the components, the apprentices who assembled the devices, the technicians who maintained them, the countless Huns whose daily labor sustained the tradition that the named engineers directed. None of those people left any record. We know they existed because the machines they built cannot be produced by a single individual. The Antikythera mechanism required metalworking, gear cutting, engraving, astronomical calculation, and precision assembly, a range of skills that no one person is likely to have possessed. It was necessarily the product of a team. That team was part of a workshop. That workshop was part of a tradition. And the entire tradition, the team, the workshop, the accumulated knowledge of generations, is invisible to history, not lost. Invisible, it was never recorded in the first place. Let that sink in. The people who actually built the ancient machines, the workers whose hands shaped the metal, whose eyes judged the alignment, whose fingers felt the tension of a properly calibrated mechanism, were, in the ancient social hierarchy, beneath the notice of the literate classes. They were craftsmen, artisans, technicians, people who worked with their hands. The Greek and Roman intellectual elite wrote about themselves, about their ideas, about their politics and their philosophies. They did not write about the workers who built their machines, any more than a modern CEO writes a memoir about the factory floor. The result is a historical record that preserves the conceptual achievements of the ancient world while systematically erasing the practical achievements that made those concepts real. We know what the machines did. We do not know who made them, how they were trained, what their workshops looked like, what tools they used, or how they transmitted their skills to the next generation. That information, the information that would allow us to reconstruct the tradition rather than merely admire its products, was never considered worth recording. This is not science fiction. This is the documented reality of how ancient knowledge was preserved and lost. The literate recorded the theoretical. The practical was left to oral tradition. An oral tradition, unlike written text, has a lifespan, measured not in centuries but in generations. 3 generations without transmission, and an oral tradition is gone. 100 years of neglect, and the knowledge of a millennium evaporates as though it had never been. The implications are staggering. If the practical engineering knowledge of the Greek world was overwhelmingly oral, then the written texts that survive, Hero's treatises, Phila's fragments, Vitruvius's descriptions, are not the knowledge itself. They are descriptions of the knowledge written by educated men who observed the machines and understood their principles, but who may not have possessed the hands-on expertise to build them. The analogy would be a music critic describing a symphony. The description may be accurate, insightful, even brilliant, but it is not the symphony, and reading it, no matter how carefully, will not teach you to play. This distinction between the knowledge and the description of the knowledge is the key to understanding why the Greek automaton tradition could not be reconstructed from the surviving texts. Hero's Pneumatica describes how his devices work. It does not describe how to train an engineer. It does not explain how to develop the feel for materials that allows a craftsman to know, by touch, whether a bearing is properly fitted or a gear is correctly shaped. It does not convey the thousands of small adjustments, improvisations, and judgment calls that separate a working machine from a pile of components. Those things, the things that make the difference between a blueprint and a functioning device, lived in the bodies and habits of the people who built the machines. When those people died without successors, the knowledge they carried died with them. The blueprints remained. The ability to read them, to translate written instructions into working mechanisms, did not. And it gets worse, because the loss of the Greek automaton tradition was not just a loss of specific machines. It was a loss of a way of thinking, a way of approaching the physical world that treated it as a system of mechanical causes and effects, susceptible to analysis, manipulation, and control. This mechanical worldview, the conviction that natural phenomena could be understood and reproduced through engineering, was the conceptual foundation upon which the entire tradition rested. Without it, the individual machines were meaningless. A steam engine is not just a collection of pipes and valves. It is an embodiment of a worldview in which heat, pressure, and motion are related by laws that human beings can discover and exploit. When the worldview was lost, when the culture that sustained it shifted its attention from mechanics to theology, from engineering to metaphysics, the machines became incomprehensible, not because they stopped working, but because the framework within which they made sense had dissolved. The medieval European monk who encountered Hero's text and read a description of automatic temple doors was not reading the same text that a 2nd century Alexandrian engineer would have read. The words were the same, the meaning was different. The Alexandrian engineer would have read it as a set of instructions, a practical guide to building a specific device using principles he understood from his training and experience. The medieval monk would have read it as a description of something approaching sorcery, a marvel that defied his understanding of how the world worked. The technology had crossed the boundary from comprehensible to magical, and once a technology becomes magical in the eyes of those who encounter it, it is, for all practical purposes, lost. You can read the words, you cannot understand them, not because you are stupid, but because you lack the context, the web of related knowledge, practical experience, and cultural assumptions that makes the words meaningful. The philosopher Thomas Kuhn, writing about scientific revolutions, argued that paradigm shifts are not merely changes in belief, but changes in perception. That scientists working within different paradigms literally see the world differently. The same principle applies to technology. The Alexandrian engineers saw the world as a system of mechanical principles. They saw pneumatic pressure, hydraulic leverage, thermal expansion, and gravitational force everywhere they looked. In every flowing river, every rising flame, every falling weight. These were not abstractions to them. They were the raw materials of engineering, forces waiting to be harnessed. When that way of seeing was lost, the world did not change, but the perception of the world changed. The rivers still flowed, the flames still rose, the weights still fell, but nobody saw machines in them anymore. Nobody looked at a fire and thought that expanding air could open a door. Nobody watched a weight descend and thought, that could drive a program. Let that sink in. An entire way of perceiving the physical world. A way that saw the environment as a reservoir of exploitable forces and the human engineer as the agent who could harness them, existed for 3 centuries in the ancient world and then vanished for 1,000 years. It was not disproven. It was not superseded. It was simply abandoned, crowded out by other ways of thinking, other priorities, other definitions of what constituted worthy knowledge. And when it was abandoned, everything it had produced, the machines, the methods, the skills, the insights, went with it. The modern world rediscovered this way of seeing independently in the workshops of Renaissance Italy and the foundries of 18th century Britain. But the rediscovery was not a restoration. It was a reinvention, a new beginning, built from scratch, without any continuity with the ancient tradition. The 1800 years between Hero and Watt were not a pause. They were a void, an absence so complete that when modern historians first encountered the evidence of ancient automata, many refused to believe it. The devices seemed impossible, not because they were impossible, but because the paradigm within which they made sense had been forgotten. The deeper truth of the Greek automaton tradition is not that the Greeks were smarter than we thought. It is that the relationship between knowledge and civilization is more fragile than we want to believe. Knowledge does not accumulate inevitably. It does not survive automatically. It is not preserved by its own importance or protected by its own brilliance. It is sustained by the specific, contingent, fragile arrangements of human institutions, economic structures, cultural values, and social relationships that give it a reason to exist and a means of reproduction. When those arrangements change, as they always, eventually, do, the knowledge they sustained is at risk. And when the knowledge is the kind that lives in hands and habits, rather than in texts and archives, the risk is not gradual erosion, but sudden, total, irreversible collapse. We are told that we live in an age of unprecedented knowledge, that the sum total of human understanding has never been greater. This is true of explicit, documented, digitally preserved knowledge. It is not true of tacit, embodied, experiential knowledge, the kind that sustained the Greek automaton tradition, the kind that produced the Antikythera mechanism and Hero's programmable theatre. That kind of knowledge is shrinking, worldwide, at an accelerating rate, as traditional crafts die, as workshop cultures dissolve, as the economic and social structures that sustained embodied expertise are replaced by structures that value only documented, standardized, transmissible information. The ancient engineers of Alexandria would recognize the pattern. They lived it. They were the products of a tradition that had sustained their knowledge for centuries, and they were the last generation of that tradition. They worked in their workshops. They built their machines. They wrote their texts. And then the world changed, and everything they knew, everything they could do, everything they could see in the fall of a weight or the expansion of heated air, evaporated into the silence of a broken tradition. The machines they left behind sit in museums and archaeological collections around the world. The Antikythera mechanism, corroded and fragmented, sits in a glass case in Athens. Replicas of Hero's devices sit in science museums from London to Washington. They are studied, admired, measured, and analysed. But the knowledge that created them, the living, breathing, hands-on expertise of the people who bent the metal and cut the gears and calibrated the mechanisms, is not in the case. It is not in the diagrams. It is not in the texts. It is nowhere. It is gone. And the most sobering realization of all is this: we cannot even be certain of the full extent of what we have lost, because the knowledge that is gone has taken with it the awareness of its own existence. We know about the machines that were described in texts, that were copied by scribes, who happened to choose them for preservation. We do not know, we cannot know, about the machines that were not described, or whose descriptions were not copied, or whose copies did not survive. The loss is not just of knowledge, it is of the knowledge of what was known. The gap is not just wide, it is bottomless. Consider one final dimension of this loss. The Greek automaton tradition was not merely an engineering tradition. It was also, in a very real sense, a philosophical tradition, an embodied exploration of questions about the nature of life, mind, and agency that philosophers had been debating in abstract terms for centuries. When Philo built a mechanical servant that responded to stimuli and adjusted its behavior, he was not just building a machine. He was building an argument, a physical demonstration that complex behavior could arise from purely mechanical causes without the intervention of soul, mind, or divine will. This argument had profound implications for ancient philosophy. The Stoics, who believed that the universe was governed by a rational, providential force, could point to the automata as evidence that rational design could produce purposeful behavior in inanimate materials. The Epicureans, who believed that the universe was the product of random atomic motion, could point to the same automata as evidence that the appearance of purpose could arise from purely mechanical processes. The automata were philosophical tools, physical arguments in a debate about the nature of reality. When the machines were lost, the arguments they embodied were lost too. The philosophical questions persisted, but the physical evidence that had illuminated them was gone. The historian of ancient philosophy, Sylvia Berryman, has argued, in her study The Mechanical Hypothesis in Ancient Greek Natural Philosophy, that the automaton tradition played a far more significant role in the development of Greek philosophical thought than most modern accounts acknowledge. The mechanistic worldview, the view that natural phenomena can be explained in terms of matter and motion without recourse to purposive forces, was not merely a theoretical position in the ancient world. It was a position supported by working machines that demonstrated, physically and undeniably, that complex behavior could be produced by purely mechanical means. The automata were not illustrations of a pre-existing philosophy. They were the evidence on which the philosophy was built. And when the evidence vanished, the philosophy lost its grounding. This is a loss whose consequences extend far beyond the history of engineering. The mechanistic worldview, which forms the conceptual foundation of modern science, was not continuously present in Western thought. It emerged in ancient Greece, supported by the automaton tradition. It was lost during the decline of the ancient world, along with the machines that had given it concrete expression. It was rediscovered, independently and painfully, in the 17th century by Descartes, Galileo, and Newton. The gap between the ancient mechanists and the modern ones, a gap of roughly 1500 years, was not a period of philosophical refinement. It was a period of philosophical regression, during which the mechanistic worldview was replaced by teleological and theological frameworks that explained natural phenomena in terms of purpose, design, and divine will rather than matter and motion. Would the mechanistic worldview have survived if the automaton tradition had survived? Would modern science have emerged sooner if the Greek engineers had not been forgotten? These are counterfactual questions, and counterfactual questions have no definitive answers. But the possibility is real, and the loss is immeasurable. The Greek automaton tradition was not just a collection of machines. It was a way of understanding the world, a lens through which the physical environment was perceived as a system of exploitable forces and mechanical relationships. That lens, ground and polished over 3 centuries of sustained engineering practice, was shattered by the decline of the civilization that had produced it. And the world that followed, the medieval world of teleological explanation and divine purpose, was, in important respects, a dimmer world. Not a world without brilliance, not a world without achievement, but a world without the specific kind of brilliance that comes from seeing the universe as a machine and yourself as its engineer. The Greek automaton builders knew something that no philosopher could articulate and no text could preserve. They knew what it felt like to make metal think, to build a mechanism so finely calibrated that it seemed to perceive, to decide, to act. They knew the uncanny moment when a collection of gears and levers and springs stops being a collection of parts and starts being a machine, when the whole becomes something greater than the sum of its components. They knew this in their hands, in their eyes, in the instinct that told them when a mechanism was correctly adjusted and when it was not. And they knew it with a depth and intimacy that no written description could capture. When those hands stopped working, when the last Alexandrian workshop closed, when the last engineer died without an apprentice, when the last machine was dismantled for its bronze, That knowledge did not fade. It ended, abruptly, silently, completely. And the silence that followed lasted longer than most civilizations endure. The modern parallel is closer than we might like to admit. We live in a world of extraordinary technological capability, a world in which machines perform tasks that would have seemed like science fiction a generation ago. But our technological knowledge is, in many ways, as fragile as the Greeks' was. The vast majority of modern technology is not understood by its users. The average person who uses a smartphone, drives a car, or flies in an airplane has no more understanding of the engineering principles involved than an ancient worshipper had of the pneumatic mechanisms behind the temple doors. The knowledge is held by specialists, by engineers, programmers, materials scientists, who work in companies, universities, and laboratories that are sustained by specific economic and institutional arrangements. If those arrangements were disrupted by economic collapse, by war, by pandemic, by any of the forces that have disrupted civilizations throughout history, the specialists would scatter, the institutions would close, and the knowledge would begin to evaporate. Imagine if every digital file on Earth were erased tonight, every database, every backup, every line of code, not the physical machines, just the information. How long would it take to rebuild? The hardware would still exist. The textbooks would still be available. The engineers would still be alive. But the specific, accumulated, iterative knowledge, encoded in billions of lines of code, the product of decades of programming, debugging, testing, and refining, would be gone. The rebuilding would take not months, but decades. And much of what was lost, the specific optimizations, the ingenious workarounds, the elegant solutions to obscure problems discovered by individual programmers working late at night and never documented, would never be recovered at all. This thought experiment is not hypothetical in its structure. It is a description of what actually happened to the Greek automaton tradition, played out over centuries rather than overnight. The hardware was recycled or discarded. The accumulated engineering knowledge was lost when the practitioners who held it died. The textbooks, Hero's treatises, Philo's fragments, survived, but they were insufficient to reconstruct the tradition, just as a shelf of programming textbooks would be insufficient to reconstruct the world's software from scratch. The historian of technology David Nye has written about what he calls the fragility of modern technological systems, the dependence of contemporary technology on supply chains, energy networks, communication systems, and institutional structures so complex and so interdependent that the failure of any one component can cascade through the entire system. The Greek automaton tradition depended on a far simpler network: royal patronage, a few workshops, a single research institution, and a modest trade in raw materials. Even that simple network proved too fragile to survive the disruptions of the late ancient world. Our networks are incomparably more complex. They are also incomparably more vulnerable. The fragility is masked by ubiquity. Because technology is everywhere, because every surface of modern life is mediated by engineered systems, we assume it is permanent. The Greeks may have assumed the same thing. The Alexandrian engineer who calibrated the mechanism of an automated theatre, adjusting the grain drain rate to achieve the perfect timing for a scene change, probably assumed that his craft would continue indefinitely, that there would always be workshops, always be apprentices, always be demand for machines that could amaze and instruct and inspire. He was wrong. The question is whether we are wrong too. And perhaps the most unsettling realization of all is that we are right now in the middle of the same process of knowledge loss that consumed the Greek tradition. Only we do not recognize it because we are inside it. The traditional crafts that connected the modern world to the material knowledge of the ancient world are dying. The workshop cultures that sustained hands-on engineering expertise are being replaced by digital design and automated manufacturing, the embodied knowledge of how materials behave. Knowledge that was once the foundation of every engineering tradition, including the Greek one, is being replaced by simulation and modeling. We are, in effect, voluntarily relinquishing the same kind of knowledge that the ancient world lost involuntarily. We are choosing to forget, and we are calling it progress. There is a final thread in this tapestry that connects everything we have discussed and gives it its full weight. The Greek automaton tradition was not merely a tradition of building machines. It was a tradition of asking questions. Questions about what it means to be alive, what it means to think, what separates the animate from the inanimate, the natural from the artificial. These questions, which we now associate with the fields of artificial intelligence, cognitive science, and the philosophy of mind, were first asked in the presence of working machines. Machines that moved, responded, and behaved in ways that blurred the boundary between the living and the made. When a worshipper watched a mechanical servant pour wine, he was not just witnessing an engineering demonstration. He was witnessing a philosophical challenge, a challenge to his understanding of what it meant to be a being that acts. When a spectator watched an automated theatre perform a complete dramatic production without human intervention, she was not just watching a show, she was watching a machine do something that had always been considered exclusively human. Tell a story. The automata were, in this sense, the first artificial intelligences, not in the modern computational sense, but in the deeper sense of artifacts that exhibited behaviours we instinctively associate with mind. The loss of these machines was not just a loss of engineering knowledge, it was a loss of philosophical provocation, a loss of the physical evidence that might have kept the questions about mind, matter, and mechanism alive through the centuries of intellectual dormancy that followed the decline of the ancient world. Without the machines, the questions retreated into pure abstraction. With the machines, they would have remained grounded in physical reality, in the undeniable, visible, tangible evidence that mechanism can produce purposeful behavior. The history of Western philosophy might have been very different if the automata had survived. If the mechanistic hypothesis had remained a living possibility, supported by working demonstrations, rather than a forgotten speculation buried in unread texts, we will never know. That is the hardest truth, and it must be stated plainly. We will never know what the Greek automaton tradition could have become, because the tradition was cut short before it reached maturity. The machines we know about, Heroes' theatres, Philo's servants, the Antikythera mechanism, were products of a tradition that had been developing for roughly 3 centuries. 3 centuries is a long time by human standards, but it is a short time by the standards of technological development. The European clockwork tradition, which began in the 13th century, required roughly 5 centuries before it produced machines of comparable sophistication to the Greek originals. If the Greek tradition had been given another 3 centuries, if the Minoan had continued to operate, if the workshops had continued to train apprentices, if the economic and political conditions had remained stable, where might ancient mechanical engineering have arrived by the 4th or 5th century of the Common Era? What machines might have existed that we cannot even imagine, because the path that would have led to them was cut off before it was travelled? The silence after that question is the deepest silence in this entire story. It is the silence of a road not taken, a future that was possible and is now permanently beyond reach. The machines are gone, the builders are gone, the tradition is gone. What remains is the evidence, the texts, the artifacts, the ruins, and the slow, mournful realization that we are not the first civilization to have been clever, and we may not be the last to forget. What does it mean that the ancient Greeks built robots? The word is deliberately provocative, but it is not inaccurate. Hero's programmable cart navigated through space, following a stored instruction set. Philo's mechanical servant sensed an input and adjusted its behavior accordingly. Hero's automated theatre executed a complex, multi-step performance without human intervention. These are, by any honest definition, robots. Machines that perform tasks autonomously, responding to their environment and following program sequences. They were built of bronze and wood instead of silicon and plastic. They were powered by gravity and compressed air instead of electricity. But the conceptual architecture, the logic of sensing, processing, and acting that defines a robot, was the same. And this realization changes how we should think about the history of technology. The conventional narrative places the origin of robotics in the 20th century, with the Czech writer Karel Čapek who coined the word robot in 1920, or with the industrial robots of the 1960s, or with the digital revolution that made modern autonomous systems possible. This narrative is wrong. The origin of robotics lies in the workshops of Alexandria, 2,000 years before Capek wrote his play. The concept, the engineering, and the working prototypes were all present in the ancient world. What was absent was the word, the industrial application, and the continuity of tradition that would have connected the ancient machines to the modern ones. The absence of that continuity is the central tragedy of this story, and it carries implications that extend far beyond the history of engineering. It implies that civilization does not move in a straight line. It does not progress steadily from primitive to advanced, from simple to complex, from ignorance to knowledge. It moves in cycles, cycles of development and decline, of discovery and forgetting, of building and losing. The Greek automaton tradition is evidence that knowledge can reach extraordinary heights and then be lost completely, not to barbarian invasion, not to ideological destruction, but to the simple, banal, everyday erosion of the conditions that sustained it. The lesson is not that knowledge is fragile in theory. The lesson is that it is fragile in practice, in ways that are invisible until the moment of collapse. This lesson is especially relevant today, as our own civilization faces pressures that echo, in some ways, the pressures that destroyed the ancient tradition. The concentration of specialized knowledge in the hands of a small number of experts. The dependence of that knowledge on institutional structures, corporations, universities, research laboratories that are sustained by economic conditions that can change. The growing gap between the producers of technology and its consumers, a gap that mirrors, in structure if not in scale, the gap between the ancient engineers and the worshippers who marveled at their temple doors. We do not have a slave economy. We do not live under the patronage of a single ruling dynasty. Our knowledge is distributed across millions of institutions in hundreds of countries, backed up in redundant digital systems and protected, we hope, by the sheer scale of its dispersal. These are real advantages. They make our tradition of knowledge preservation far more robust than the Greeks ever was. But robustness is not invulnerability. And the specific kind of knowledge that the Greek tradition embodied, the tacit, embodied, experiential knowledge of how to work with physical materials, is not protected by digital backup systems. It lives in people. And people, as the ancient world demonstrated with devastating finality, are mortal. The reflection that this story demands is not one of despair. It is one of awareness. The Greek automaton tradition existed. It flourished. It produced marvels. And it died. Not because it was weak, but because the conditions that sustained it were not permanent. Our own tradition of technological knowledge exists, flourishes, and produces marvels that would stagger the imagination of Hero or Ctesibius or Archimedes. Whether it will endure is not a question of intelligence or capability. It is a question of whether we maintain the conditions, the institutions, the training, the funding, the cultural respect for practical knowledge that sustain it. The ancient engineers could not have saved their tradition alone. By the time the decline was visible, the forces driving it were too large and too impersonal for any individual or group to resist. But they might have recognized the danger sooner if they had understood the fragility of what they had built. Not the machines, which were sturdy enough, but the tradition that produced them, which was as delicate and as irreplaceable as any mechanism they ever assembled. We have the advantage of hindsight. We have the example of the Greeks before us, a civilization that reached the frontier of mechanical engineering and then lost its way. The question is whether we will learn from their example or repeat it, whether we will recognize, before it is too late, that the knowledge held in human hands and human habits is as worthy of preservation as the knowledge held in human texts and human databases. Whether we will understand that a tradition of practice, sustained over generations by the patient labor of skilled practitioners, is not a relic of the past, but a lifeline to the future. The machines of Alexandria are gone, but the warning they left behind is still speaking. The only question is whether we are listening. In a glass case in the National Archaeological Museum in Athens, there is a corroded lump of bronze, roughly the size of a large shoebox. Most of its gears are fused together. Its surfaces are covered with a green patina that obscures the fine inscriptions etched into the metal. To the casual visitor, it looks like a piece of debris, something hauled from the sea and placed under glass for reasons that are not immediately obvious. This is the Antikythera mechanism. It is the most sophisticated mechanical device known to have survived from the ancient world. It computed the motions of celestial bodies with a precision that was not matched in Europe for 1500 years. It represents a tradition of gear cutting, mechanical computation, and precision engineering that was fully developed, widely practiced, and then completely forgotten. It sits in its case, silent and still, surrounded by marble statues and painted vases. The kinds of ancient artifacts that we know how to appreciate, that fit neatly into our understanding of what the ancient world produced. The mechanism does not fit. It challenges. It unsettles. It sits in the same museum as the classical sculptures of the Golden Age, but it belongs to a different history. A history of engineering rather than art, of mechanical intelligence rather than aesthetic beauty, of a civilization that was building machines while we were taught it was building only temples. The answer to the question in the title is simple, and it is unsettling. Greek automata should not have been possible, not according to the story of technology that we grew up with, the story that places the origin of mechanical ingenuity in the workshops of the Renaissance and the factories of the Industrial Revolution. According to that story, the ancient world was pre-technological, a world of hand tools, animal power, and simple machines. That story is wrong. The ancient world was a world of programmable devices, feedback mechanisms, steam engines, and precision-geared computers. It was a world in which named engineers, working in funded institutions, produced machines whose operating principles are identical to the principles that drive modern robotics and modern computing. The machines were possible because the Greeks combined three things that had never been combined before: mathematical sophistication, engineering ambition, and institutional support. They had the theory, a tradition of mathematical reasoning that allowed them to model the physical world with precision. They had the skill, a tradition of metalworking, woodworking, and precision manufacture that allowed them to realize their models in physical form. And they had the patronage, a system of royal funding and institutional support that allowed them to pursue their work over decades and centuries, building on the achievements of their predecessors and transmitting their knowledge to their successors. When that combination dissolved, when the mathematics continued but the engineering declined, when the skill persisted but the patronage evaporated, when the knowledge survived in texts but died in workshops, the tradition ended, not with a bang, not with a fire, not with an army at the gates, but with the slow, quiet extinction of a way of working, a way of knowing, and a way of seeing the world that had produced some of the most extraordinary machines in human history. The machines they left behind are still here. The Antikythera mechanism corrodes in its case. Replicas of heroes' devices click and whir in science museums. Scholars publish papers analyzing the gear ratios of mechanisms that no one can build in their original form. The artifacts endure. The tradition that created them does not. If all the machines of the ancient Greek engineers could be assembled in a single room, every automated theatre, every programmable cart, every singing bird, every self-opening door, every steam-powered sphere, every geared computer, every coin-operated dispenser, the room would contain a collection of devices whose combined engineering sophistication would rival a modern science museum. That room was never built, but the machines it would have contained were real. They worked. They demonstrated principles that we now consider fundamental to modern technology, and every single one of them was forgotten. There is a sentence attributed to the medieval philosopher Bernard of Chartres, that we are like dwarfs sitting on the shoulders of giants, able to see farther than they could because of the height on which we sit. The metaphor is usually taken as a celebration of intellectual progress, each generation standing on the achievements of the last, seeing farther, knowing more. But the metaphor contains a hidden assumption that the shoulders are still there, that the giants endure, that the knowledge of the past is a stable platform on which the present can stand. The story of the Greek automata reveals that the shoulders do not always endure. The giants fall, the knowledge crumbles, and the dwarfs who stood on them tumble into a darkness from which it takes centuries to emerge. The Greek engineers were giants, intellectual and mechanical giants whose achievements set the foundation for a tradition that could have changed the world. They fell, the tradition fell with them, and the world that followed, the world that emerged from the rubble of the ancient through the long medieval centuries and into the bright, loud, confident modernity in which we now live, is a world that had to learn again, from scratch, what the Greeks already knew. Every gear in the Antikythera mechanism was cut by a human hand. Every chord in Hero's automaton theatre was tied by human fingers. Every valve in Ctesibius's water organ was fitted by a craftsman who knew, by touch and by sound and by the accumulated experience of years, when the fit was right. Those hands are gone. Those fingers are dust. That craftsman has no name and no grave. But the machines he built still speak, corroded, fragmentary, incomplete, from their glass cases and their museum halls, telling anyone who will listen that the ancient world was not what we thought it was, that it was vaster, stranger, more brilliant, and more fragile than we imagined, that it built wonders, and that it forgot them. The Greek automata should not have been possible, but they were. They were possible because a civilization chose to invest its wealth, its talent, and its intellectual ambition in the systematic exploration of mechanical principles. They became impossible again, or rather, they became forgotten, because that same civilization allowed the conditions that had sustained the exploration to wither and die. The machines did not fail. The civilization failed the machines. The Antikythera mechanisms ticks in the imagination of everyone who has ever stood before it. Not the ticking of gears. Those have been silent for 2,000 years. But the ticking of a question that will not stop. What else did they build that we will never find? The mechanism does not answer. It sits in its case, silent, corroded, patient, waiting for someone to build what it can no longer demonstrate. The knowledge is gone. The bronze remains.